plasmalemma functions as a receptor for the cell. Plasmalemma is your cell membrane. Okay? Plasmalemma has receptors specific for chemical stimuli, electrical stimuli, and mechanical stimuli. Not all plasmalemmas have the same receptor sites. Different cells respond to different stimuli. Okay? But all cells will function and respond to certain stimuli. Okay? So sensory information arrives, it's picked up by the sensory receptors. Just so we have a stimulus, the sensory receptors pick up that information. Something's got to pick it up. Something's got to tell you it's hot. Something's got to tell you it's sharp. Something's got to tell you it burns. It picks up that information. And it sends it up through the afferent system and through the dorsal horn of the spinal nerve. Okay? So sensory receptors are the interface between the nervous system and the internal or external environment where it's picking up your stimuli. Okay, there's different types of senses. There's general senses. General senses refer to temperature, pain, touch, pressure, vibration, proprioception. Okay, and special senses like smell, taste, your balance, hearing, vision. Okay, so you have general senses, and then you have very specialized senses. Special sensory receptors are located in complex sense organs, like your eyes, your ears, your taste buds. Those are all complex sense organs. The rest of the other general senses are just a simple pressure receptor or simple temperature receptor. Okay? They're much more specialized, much more complex when you're dealing with the special senses, with hearing and sight or taste. Each receptor has a characteristic sensitivity that leads to receptor specificity. Every receptor has a certain specificity it will respond to. Specificity is due to the structure of the receptor. Everything works on the three-dimensional shape of the receptor. A certain receptor will bond to an area by its three-dimensional shape through hydrogen bonding. Okay. Examples of specificity. You can have free nerve endings. Okay. Free nerve endings are the simplest circuit you have. It says the nerve has an ending on it and it responds to a variety of stimulus. Something hot, to pressure, to pain. Okay. Or you can have something very complex, like receptors of the retina. Okay. In the retina, responds to specific and responds to light only. Okay. The retina doesn't respond to sound, doesn't respond to pressure, temperature. It responds to light. It gives you an image that is transmitted into the brain so you can see what's out in your environment. Okay, so it's a very specific receptor. Okay, the area monitored by the receptor is called the receptive field. This is the area where you can feel the impulse or feel your stimuli. Okay, receptive field. You have a very large receptive field. So if you have this huge field here, and you got a receptor here, receptor here, receptor here, receptor here, okay? You can tell roughly where something is. You can't pinpoint it exactly. You got a huge field and a couple of receptors. So if you get a stimulus, you know it's in this area somewhere. If you got a very small field and you have receptors, like 5 receptors, let's say the other one, okay? Now you can pinpoint where something is, okay? You can easily locate a stimulus if the receptive field is small. If you have a lot of neurons in that receptor field, because each neuron's going to send an impulse to the brain. So if this neuron fires, you know it's going to be right here. Okay, so if you're going to fire a neuron, it's going to be right at this spot. You know that. If you fire anywhere around this one right here, that's going to fire that neuron. So you know it's going to be in that general area. You're not as specific. So a large receptor field, have receptors spread far apart, makes it difficult to localize exactly where stimulus comes from. Because if we find that, you know it's in that area. But a small receptor field, have receptors close together, so you can easily localize. If that neuron fired, you know exactly where that was in that receptor field. Okay, so large fields, you can get an idea where it is, but you're not very localized. Small receptor fields, you know exactly where it's coming from. So there's receptor field, and you see the neurons underneath it, how they innervate the area. Go back to red there. Okay. So information is relayed from the receptor to a specific neuron in the central nervous system. Let me make sure it's still should be recording. Let me just double check since I didn't turn anything off. Yeah, still doing. Okay. So interpretation of the sensory information is relayed from the receptor to a specific neuron in the central nervous system. Each pathway carries information that concerns a specific sensation. So you got a pathway for heat, pathway for pain, pathway for pressure, so you know what you're feeling and where it's coming from. The identity of the active neuron indicates the location of the stimulus and the nature of the stimulus. Okay? So you know where you're feeling the pain, and you know what type of pain you're feeling. Okay? Those are your sensory information from the receptor site. Okay, there's different types of receptors. There's two types. There's one called tonic. There's tonic receptors and there's phasic receptors. Tonic receptors are always active. They're always on. Tonic receptors are always on. What can you think of that's always on? Hearing. If you're sitting there at the desk, reading a book, whatever, and someone drops a glass behind you, you turn that direction because they're a tonic receptor. They're always on. Eyesight. If you're looking at, watching me talk, and one of your kids runs by in the corner of the room and you see out of the corner of your eye, okay, that's always on. That's a tonic receptor. Photoreceptors of the eye, receptors that constantly monitor body position. Okay, proprioceptor receptors. Like when you're sitting here listening to me talk and you fall asleep. You're sitting at your desk, you're looking at me, and all of a sudden your head goes down to the desk. You got that receptor until your head is falling, and you snap your neck and you wake back up. Okay, those are tonic receptors. They're always on. They're always doing something. You always know where your body is, where parts of your body are. You know where it's balanced. Okay, phasic receptors. Usually they're not turned on. They're inactive. They become active when it's necessary. So they activate for a short time and they turn back off. They're usually off, but then you need them to come back on, like touch and pressure for the skin. Okay, if you touch something, you know you can touch it and it goes on and then off again. Okay, you get an initial feel and then that feeling just goes away with time. It adapts to it. That's your phasic receptors. Okay, so central processing and adaptation. Okay, adaptation is reduction in sensitivity due to a constant stimulus. Okay, if you take your hand and you put it and you squeeze on the desk, you feel the pressure there. If you keep squeezing, that pressure gets less. The adapters get used to it, okay? They adapt to it. Just when you walk outside when it's cold at first, like in the desert, if it's like 75 degrees, you put a jacket on, right? When you're from 29 Palms. Okay, but you're out there for a while, you adapt to it. People in Michigan or people in Ireland, they'll go outside, 40, 50 degrees, and they'll think it's a great day for a short sleeve shirt. Out here, we wear 2 jackets, long underwear, and everything. Okay? You adapt to your conditions, okay? That's adaptation. Peripheral adaptation. Receptors respond strongly at first, then they decline. Okay? When you first get a reaction to something, you respond to it real quick, and then that response declines. It's a peripheral adaptation to it. And you have central adaptation. Okay, that's adapted within your central nervous system. You're constantly aware of the stimulus, but it quickly dissipates or disappears. Okay? You're aware of something and then it phases out. So those are types of adaptation. You have adaptation, peripheral adaptation, and central adaptation. Okay. You have classification of general senses. Okay. There's exteroceptors, proprioceptors, and interoceptors. Okay. Your exteroceptors. Okay. These provide information about your external environment. They're exteroceptors, let you know what's going on outside your body. Proprioceptors, information about the position of your body, where you're at. Like you said, you can stick your arm out, close your eyes, you know where your hand is. Okay, you don't have to see it. That's your information about the position of your body. You know where all the body parts are at all given times. That's proprioception. Okay, interoceptors, information about the inside of your body, the pH of your bloodstream, amount of carbon dioxide in your bloodstream, if you need to take another breath, your heart rate. Those are all interoceptors, information about the inside of your body. So exteroceptors, interoceptors, outside the body, inside the body, and proprioceptors, where your body is positioned at all times. Okay, other ways of classifying the general senses. They can be nociceptors, thermoreceptors, mechanoreceptors, and chemoreceptors. Nociceptors, receptors that respond to pain. Thermoreceptors respond to temperature. Mechanoreceptors activate by physical distortion of cell membrane, mechanical pressure, distortion of the cells. Chemoreceptors monitor the composition of body fluids. Okay, the chemical composition. So it's pain, temperature, mechanics or pressure, and chemicals. That's another way of classifying your general senses. So nociceptors, those are your pain receptors we just talked about. They usually have free endings and have very large receptor fields. So nociceptors, you know it's pain, but you don't know exactly where it's coming from. Okay? If someone does a pinpoint on your back, you can localize the area, but you can't tell exactly where it's coming from. It's such a large pain receptor field. It makes it difficult to pinpoint the location of the origin of pain. There's three types that are pains that are sent to extreme temperature, mechanical damage, and chemical damage. Those are all nociceptors. And those are just your large fields, so you get an idea of where the pain is coming from. They also have fast pain, slow pain, and referred pain. Referred pain is really important working in the emergency room or working with patients. Okay? Fast pain, sensation reaches the central nervous system extremely quickly, associated with a prick or cutting. Okay? Slow pain, sensations reach the central nervous system slowly. Okay? Burning or aching feels, aching pain. It gets into it a lot slower. All right, referred pain is when sensation reaches the spinal cord by the dorsal root. Remember, the dorsal root, okay, is where your afferent nerves enter the spinal cord. Okay, that's your sensation. Now, some of your organs may reach the spinal cord through the same dorsal root. Okay. In other words, it's traveling on the same path, so the brain can interpret that pain coming from a different area. Say the most common one is the heart and your left arm. If you have pain in your left arm, that left arm signals pain coming up, okay? And the same nerve tract from the heart follows that in to the dorsal root of the spinal cord, okay? So the body feels the pain here, but the pain is actually coming from your heart because it's combining into the same nerve tract. Okay, so your heart, if pain travels down your left arm, you have a patient coming to your clinic, blood pressure says 170 over 110. They're kind of in distress, they're sweating, they have pain, and their left arm goes numb and starts to become pain radiating down their left arm. Okay, if that walks into your clinic, you call an ambulance. You don't wait, you don't delay, that's referred pain. Okay, you get them to an ER immediately because that is a really good chance to get a heart attack. That's the most common one we see. I had one in the dental office probably 7 years ago now. Came in for filling. We took his blood pressure, it was high. He started sweating. He goes, you know what? My left arm's starting to tingle and it feels really painful on here. Ambulance is called that second. No more talking. Goes to the patient doesn't have a choice. They go to the ER. Now they can walk out of the office and go, hey, that's your choice, but they go to the ER. He has a heart attack. I mean, that's what you look for. That's referred pain. The liver and gallbladder can refer up to the right shoulder. The stomach refer from this area, intestine, appendix, colon can all refer into this area here. They all combine into that area. The ureters can cause pain, can cause this lower back pain that wraps around your back. Kidney stones. Anybody have kidney stones? Extremely painful, lower back pain right around that area. Those kidneys block it, the same receptors. That's where the pain, the brain can interpret the pain from coming from. Like I said, the one you're going to be concerned about in an ER situation is right here. Because if you got a patient that's actively having a heart attack, you don't want to play with that. Okay, that's the left arm. It's one thing. If you learn anything from this class, learn that. If you're working as an RN or something, and you got a patient with pain going on the left arm in distress, treat him as a heart attack. You can always go back later and fix something else, but treat it as a heart attack because that's referred pain. All right, pain receptors there. These are thermoreceptors. Thermoreceptors are temperature. They're found in the dermis, skeletal muscles, your liver, and your hypothalamus. All temperature. Cold receptors are more numerous than hot receptors. They exist as free nerve endings. Okay, they're phasic receptors. Phasic means what? They're usually off. Okay, they get turned on during the stimulus, and you adapt to them, and they get turned off. They're very active when the temperature changes, but quickly adapt to a stable temperature. Okay, if you're outside and the temperature drops 5 degrees, it gets cold really quick, but then after about 5 minutes or so, you don't even notice it. Okay, your body adapts to it. They're phasic receptors. They come on when they need to come on. Mechanoreceptors. Receptors are sensitive to stretch, compression, twisting, distortion of the plasma lemma. Okay? Those are the ones that cause charity horses, cramping in your legs. When you get up in the morning, you stretch those legs. You ever get a charity horse and you start stretching your legs? That's because of those mechanoreceptors. Okay? The muscles are being stretched, they're being distorted, so being distorted. The body's saying, no, we're not supposed to do that. And they contract. And they contract so much they clump up that muscle. And those can be very painful. But there's 3 types of mechanoreceptors. There's tactile receptors, there's baroreceptors, and there's proprioceptors. Okay? We already know what proprioceptors are. We talked about that. Tactile receptors provide a sensation of touch, pressure, vibration. That's your tactile sense. Okay? They have unencapsulated tactile receptors, which means they're free nerve endings. It's a tactile disc, like a root hair plexus. Okay? Like when the wind blows over your hair, you know, you can feel it. You can feel your hair moving. Okay? That's a sensation of touch or pressure on your hair. Like an insect crawling on your arm, it stimulates the hair receptors. Okay? It gets those unencapsulated tactile receptors. The encapsulated tactile receptors are called tactile corpuscles, Ruffini corpuscles, and lamellated corpuscles. And there's nerve ending with an encapsulation around it in different shapes, depending on what the pressure is going to be used to detect. Mechanoreceptors are the tactile receptors. Free nerve endings are common in the dermis, because you can tell when you're touching something. Tactile discs are in the stratum basale layer of the epidermis. Root hair plexus monitors distortion and movement of the body surface. Okay. So here's the different types of receptors. This is a free nerve ending. Right here, you can see where it's just a nerve ending that ends right there. Okay. This is a tactile corpuscle. You can see it has a encapsulated on over it. You have Merkel cells and tactile discs. Okay. So they're smaller ones, but they have the endings encapsulated on them. This is the Ruffini corpuscles. Ruffini corpuscles are an odd shape. If you have kids, have you ever seen a show called Hey Arnold? He's a football-shaped head guy watching the grandkids. Ruffini corpuscles look like Hey Arnold. They got that sideways football look to them. Okay, and then lamellated corpuscles. You can always tell laminated corpuscles because they're concentric rings, like tree rings. Laminated means ring by ring by ring. And it's called a laminated corpuscle. So laminated corpuscles and Ruffini corpuscles are 2 very distinct ones you can tell. The Merkel cells and tactile discs are very small and have little encapsulation. The tactile corpuscles are large encapsulated corpuscles, encapsulated nerve endings, and you have free nerve endings. Okay? And that's your sense, that makes like your sensory, and this is the sensory nerve coming in. So information, this is an afferent nerve, and it goes out. And this is a view of free nerve endings in the epidermis. You can see all those different free nerve endings there that can transmit down along this nerve right here, this afferent nerve. Again, the nerve endings are always afferent. They're sensory nerve endings. Okay, there's no motor coordinating with these input. They're just sensory nerves. You can see the Merkel cells, the tactile discs again. You can see the free nerve endings around the root hair plexus. Again, you can see the Ruffini corpuscles, the laminated corpuscles, tactile corpuscles, all have distinct shapes. Okay, so mechanical receptors, mechanical distortion of cells with pressure. The tactile corpuscles are common on your eyelids, your lips, your fingertips, nipples, and genitalia. They're very sensitive. They're for tactile sense. Ruffini corpuscles are in the dermis. They're sensitive to pressure and distortion. And the laminated corpuscles consist of concentric cell layers. Those are the rings we talked about. And they're sensitive to vibration. Those rings sense vibrations on those. Okay. And you can see the tactile corpuscles again. Okay, on the light microscope, you see the tactile corpuscles black up, and then up in the dermis below it. So this is your tactile corpuscle, and this is your sensory nerve fiber. Information, and then that nerve fires and connects it into the central nervous system. Okay, again, you have the Ruffini corpuscles, which are the ones that are kind of football shaped. So this is your sensory nerve fiber right here. Okay, so collagen fibers hold in place. These are the dendrites. Stimulation comes into the receptors here on the dendrites. Once it reaches a threshold level, that impulse gets sent down the nerve fiber as a sensory nerve into the central nervous system. Okay, this is the laminated corpuscle, and you see the concentric layers. You see this light microscope picture, and it's just like a tree. That's like a tree trunk. When a tree's been cut, you can see the concentric layer. It's called lamellated. Okay? Okay, this is the dendritic process inside of it. Once this is activated by the pressure distortion against all these little circles here for vibration, this gets activated, reaches the threshold, sends the impulse down the axon into the central nervous system. Baroreceptors. Baroreceptors are organs that monitor change in the stretch of an organ. And they're located where you would expect, the stomach, so you can tell when you're full. The small intestine, the urinary bladder, so you can tell when it's filled up. Those things stretch, and you have to have receptors that tell your brain when they've reached their limit. So stomach, small intestine, urinary bladder, the carotid artery, the lungs, the large intestine, are all things that when they stretch, you need to know about it. Your body has to respond. If the lungs keep stretching and stretching, your body has to respond by saying, hey, you can't keep inhaling that deeply. And the body constrict the lungs, or the large intestine, or the urinary bladder. It tells your brain it's full. Okay? So those are your baroreceptors that tell you when things have stretched to a certain limit. Okay, so here's the different baroreceptors. Okay, the carotid sinus and aortic sinus provide information of blood pressure to your cardiovascular system. Okay? Too much blood, too little blood, high blood pressure. Baroreceptors of the lungs provide information on lung stretching. Okay, to respiratory rhythmic centers for control of your respiratory rate. Baroreceptors of the digestive tract. Okay, the volume of what is filled with materials will stretch. Baroreceptors of the colon, that's your large intestine, triggers defecation reflex when it gets filled. And of the bladder walls, the urinary bladder. When it starts to get filled, it triggers a urinary reflex. Okay, those are all baroreceptors. It allows the body to sense when something's being stretched. That tells you it's full or something's happening, and you have to counteract it. Mechanical receptors are proprioceptors. That tells you where your body is in space and time. Okay, it monitors the position of your joints. It knows where all your joints are. Okay, if you're going to stand, your joints have to support that, your knee joints. Okay, if you're going to sit, your knee joints don't. If you stretch your arm out, your elbow joints have to support that. So you have to monitor the position of your joints to tell where your body is. It monitors the tensions in the tendons and the ligaments. Now, tendons connect what? Remember this from the first chapter or second chapter? And ligaments connect what? Tendons connect?
Muscle to bone.
Muscle to bone. Perfect. Ligaments connect?
Bone to bone.
Bone to bone. What's the one that connects muscle to muscle?
Aponeurosis.
Aponeurosis. Perfect. All right. That's exactly right. So the Golgi tendon organs are the receptors in the tendons. These are the ones that respond to stretching in the tendons. Okay? It monitors the length of the muscle fibers when it contracts, and the muscle spindles are in the receptors in that muscle. So that you know when that muscle contracts, how much it can contract without it damaging. Chemical receptors detect small changes in concentration of chemicals in the body. They respond to water-soluble, lipid-soluble compounds. They're found in respiratory centers, medulla oblongata, carotid arteries, the aortic arch. These are different areas where we have to monitor our pH. We have to monitor our partial pressure of CO2 to trigger our breathing. So these are chemical receptors that have to be able to tell what's going on in the body so we can monitor it to keep our homeostasis. So chemoreceptors in the respiratory centers of medulla oblongata are sensitive to pH and a partial pressure of CO2 in cerebrospinal fluid. Okay? If those change, it triggers a reflex adjustment in the depth and rate of your respiration to control your pH because of the carbonic acid that carries the CO2 and the partial pressure of carbon dioxide. Chemoreceptors, the carotid arteries, are sensitive to pH, CO2, and partial pressure of CO2 and partial pressure of oxygen. Okay, and those go to cranial nerve number 9, and they trigger reflex adjustments in the respiratory and the cardiovascular center to bring those values back to normal. And chemoreceptors in the aortic bodies are sensitive to changes in pH, partial pressure of CO2, and partial pressure of oxygen in the blood. Okay? And those go through the 10th cranial nerve, the vagus nerve. And those trigger reflexes in the respiratory and cardiovascular system to adjust those values also. Okay? Our values can't get too far off, our pH especially. pH of blood is extremely important because all our enzymes function within a certain pH region. If your body goes too high or too low, we got all kinds of diseases that occur from that. All right, olfactory epithelium. When we talked about this with the cribriform plate, with the ethmoid bone, we talked about the olfactory bulbs and things like that. The olfactory epithelium consists of olfactory receptors, supporting cells, basal cells, and olfactory glands. Okay, so here's your olfactory pathway. Okay, you got your olfactory epithelium, which is the lining where the nerve receptors fit into. That's your epithelium. Okay, you got your olfactory nerve fibers, which is cranial nerve number 1. Then you got your olfactory bulb, with those fibers feed into. And then from the olfactory bulb, as those nerve fibers run through the cribriform plate of the ethmoid bone. Then you got your olfactory bulb, feeds into the olfactory tract. The olfactory tract goes into the central nervous system. Okay, and you see the cribriform plate. Cribriform plate is what all those holes, those little tiny holes in the bone of the sphenoid bone. Okay. You see how they all connect in and travel through that. And there's 3 bony areas on the nose that help circulate the air and trap pathogens. That is your inferior nasal concha, your middle nasal concha, and your superior nasal concha. Okay, that's all for air design when you breathe through your nose. Okay, you can see all the different, this is the substance, oh, I'll come back. This is your substance being smelled right here. These little particles to get to the nose fibers. And these are the fibers. This is your olfactory epithelium, which surrounds the fibers. You have the lamina propria, which is your base for the epithelium. Then you have the cribriform plate, which is the holes through this sphenoid bone. Okay. So these are your olfactory nerve fibers. So this is your actual cranial nerve number 1, right here. That's CN1. Those are your olfactory nerve fibers that feed up into the bulbs, and from the bulbs it goes into the sensory tract, olfactory tract. So the olfactory pathway, axons leave the olfactory epithelium. They pass through the cribriform foramina, the cribriform plate, all those little openings. They synapse on neurons in the olfactory bulbs. That impulse travels to the brain through cranial nerve number 1. That's your olfactory nerve. Arrives at the cerebral cortex, goes to the hypothalamus and the limbic system. Now the limbic system is your emotional system, which is responsible for storing memories. That's why it goes in the same area as the limbic system. That's why certain smells invoke certain memories. Okay, if your wife has a certain perfume that she wears, that memory is involved by that smell. It's going to the same system. It's going through the limbic system where we store memory. So memories are stored along with smells and emotions. But there's certain emotions bring back certain types of memories also. Okay, they're all stored in the limbic system, which is your memory and your emotion system. And that's where the olfactory pathway goes. Okay, same picture we just saw. Okay, the olfactory epithelium, olfactory nerves. You have goes to olfactory bulb, olfactory tract into the central nervous system, the hypothalamus and limbic system in the cerebrum. Okay. Discrimination, how we smell different smells. The epithelial receptors have different sensitivities, so you can detect different smells that way. Olfactory receptors can be replaced. The replacement activity declines with age. So they'll not be replaced, so your sensitivity to certain smells decreases with age. Just like everything else in the body. After 21, it's all downhill. Gustation. Gustation is taste. The tongue consists of papillae. Papillae consists of taste buds. There's 3 types of papillae on your tongue. There's filiform, which is the very small, very tiny ones. There's fungiforms, which is a little bit larger ones. Then there's circumvallate papillae, which are really huge ones in the back, like little mushroom pads in the back. Okay? Taste buds consist of gustatory cells. Okay? So that's what the different types of taste buds look like.
They're past Amway already.
All right.
8:30.
Cool. See them and my grandkids are on the way. They're coming on to visit for the weekend. So they're there in Amboy. She's just keep me informed. All right, so circumvallate papillae, the very large ones at the base of the tongue. And you see them on the very back of your tongue. And they look like little mushroom pads, little stalks back there. Okay, the fungiform are the larger ones. And the filiform are the real little tiny ones on the cover of the tongue. And the different types on different areas of the tongue have different sensitivities for different tastes. Like your sour taste at the very base back of your tongue. That's where you taste sour. More towards, then you taste bitter, salty, and sweet towards the tip of your tongue. Okay, so different thing. Those are your circumvallate papillae. You see those things look like huge pads here, right there. That's your circumvallate papillae. Those are your very large ones. Okay, along the base of the tongue. Okay, this is your fungiform papillae, the ones with the circles around it. Okay, you see there's a large one right there. There's a large one right there. You see they're a little bit larger. You see the bigger bumps. Okay, those are your fungiform. And all these little bumps right here, these tiny little bumps, those are the filiform papillae. So there's three different types of papillae, the circumvallate, the fungiform, and the filiform. And you identify those. They're easily identified by their different sizes. Okay, so taste buds consist of gustatory cells. Each gustatory cell has a slender microvilli. Remember what a microvilli is? It sticks up, kind of waves out there, extends through the taste bud pore into the surrounding fluid. So the villi increases surface area tremendously and can absorb what's around it. So dissolved chemicals contact the microvilli. Okay. This provides a stimulus that changes the transmembrane potential of the gustatory cell and sends a nerve impulse down. And if it changes it in a certain area, it tastes the different types of taste, whether it's sour, sweet, bitter, etc., or salty. So the stimulus provides a change in transmembrane potential. That information goes to the brain, and that gets interpreted as taste in the cerebral cortex. So dissolved chemicals contact the taste hairs. Those are your microvilli, stick through the pore. Impulses go from the gustatory cells through cranial nerve number 7, number 9, and number 10. Synapses the nucleus solitarius of the medulla oblongata is where it goes into. Then it sends that into the medial lemniscus, and it synapses into the thalamus. Okay. From the thalamus, it sends information into the gustatory complex. Remember the insula. The gustatory complex is around there, and it sends information to there. The thalamus is the main, that little egg-shaped nucleus, that's the main area where everything gets distributed into the cerebral cortex, where it has to go. And it sends into the insula sus, we have gustatory cortex. Okay. Again, there's the vagus nerve, there's the glossopharyngeal nerve, and the facial nerve. They all transmit the information from the tongue, okay, into the nucleus solitarius. Goes to the medial lemniscus, into the thalamus. Thalamus then goes into the gustatory cortex, which is in the insula, part of the brain. So we begin life with more than 10,000 taste buds. Okay. By age 50, okay, the number has declined rapidly. Okay. Coupled with decline in olfactory receptors, taste diminishes as we age. So we lose a sense of smell, and if you don't have a sense of smell, you don't have taste either, and you lose sense of taste. So the threshold level is low for gustatory cells responsible for unpleasant stimuli. So something that tastes really bad or smells really bad, the threshold value is very low. You only need a little bit, and your body tells you something's wrong, this does not taste good, and you spit it out instantly. Threshold level is high for stuff that tastes pleasant, because if it's pleasant, it's not going to hurt you. If a poison or something that's going to be very unpleasant, your body knows it immediately and doesn't swallow it. Okay? So very low threshold for unpleasant stimuli, high threshold for pleasant stimuli for your gustatory discrimination. Okay. There's 4 primary tastes, probably 6. They added 2 more recently. The 4 basic tastes are sweet, salty, bitter, and sour. Those are your 4 basic tastes. You also have what's called umami, which is a savory taste, like a beef or chicken broth. Okay? Or you have a water taste. Looking at what taste, so you know when you're thirsty. Those are the 2 that they added. But your 4 main ones are sweet, salty, bitter, or sour. And then umami, which is savory, and then water. Okay? That's your gustatory system. Equilibrium and hearing. Okay? Structures of the ear are involved in balance and in hearing. Your ear controls equilibrium and controls what you hear. The ear is divided into 3 regions: the external, the middle, and the internal or inner. So external ear, middle ear, inner ear. Okay? And this is a representation of the different areas. You can see this is the external ear. Where's my pointer? There we go. This is your external ear up to this area. This is your middle ear, which is the white area right here. And the other gray area is your inner ear. Okay? The inner ear has an auricle, which is your cartilage outside. This is your elastic cartilage. It's the outer part of your ear. You have the external acoustic meatus, which is the external opening of the ear. Your external acoustic meatus, we learned on the skull, that's in the temporal bone. Okay, that's your external acoustic meatus. Going across that, you have your eardrum. Your eardrum is called the tympanic membrane. This blue diaphragm thing right here is your tympanic membrane. That's your eardrum. Okay. And behind the eardrum, you have the tympanic cavity. Inside that tympanic cavity, you have these three auditory vesicles or ossicles. Okay, those are the three small bones of the ear: the malleus, the incus, and the stapes, in that order. Okay. And then we have the stapes. After the ear, the sound is transmitted from the malleus to the incus and the stapes. Okay, this is the oval window where the stapes connects to, and below that is the round window where sound can reverberate through. Okay, then you have this tube. Okay, this is the auditory tube, connects your inner ear to your nasal pharynx, to the oral cavity. That way, pressure, you can equalize pressure because this is sealed. Okay, if this was sealed, it would gain pressure and build up pressure, and you couldn't equalize it. Okay, you have this tube that runs in the oral cavity, so when you yawn, get air in, or swallow, that equalizes the pressure in your inner ear. If you're a scuba diver, what do they have you do? Every 20 feet or so, you grab your nose and you blow, right? That allows air to go into the auditory tube, and it equalizes the pressure in the inner ear to what you're breathing in your scuba tanks. So your ears don't pop, don't hurt underwater. Okay? If this becomes blocked, like when you have a cold and you're traveling in an airline passenger jets are pressurized about 7,000 feet. Okay, if you have a blocked blocked auditory tube, you can't pressure your lines, you'll have a tremendous earache when you fly. You got to be able to pressurize your tube when the pressure changes, pressurize that internal ear. We have the oval window. On the inner ear, you have the semicircular canals, which are these areas that go like a canal that goes up and around in circles. Okay, that causes certain types of sound. You have the preter's bone or the temporal bone. This is your temporal bone. This is the preter's portion of it. You have facial nerve and the vestibulo-ocular nerve, number 7, number 8. They run right through that above the cochlea. Cochlea is your snail-shaped structure. Okay, there's nerve 7, there's nerve 8. Okay, and that's what we want to see on that. Okay, so the external ear consists of your auricle, consists of the external acoustic meatus, tympanic membrane, and the ceremonous glands. Ceremonous glands produce cerumen, which is earwax. Okay, so these are the parts of the external parts of the ear: the auricle, the external acoustic meatus, and the temporal bone, and the tympanic membrane, which you can see right there. Okay, ceremonous glands are a type of apocrine gland. Where we have apocrine secretion. Okay. Location is the outer ear, and it secretes cerumen, which is earwax. It's located subcutaneously in the outer 1/3 of the external auditory canal. So it's located in the 1/3 closest to the outside of your skull, and that 1/3 of it is where that's located. The glands are located. That produces your earwax. The middle ear. Middle ear consists of your tympanic cavity, which is just behind the tympanic membrane, which is your eardrum. The auditory ossicles, the 3 smaller bones of the middle ear, the malleus, the incus, and the stapes. And they're in that order too. The malleus is first, connects to the incus and connects to the stapes, and the stapes connects to the oval window. You have the auditory tube, which is a pharyngeotympanic tube. It connects the pharynx to the tympanic cavity. And you got muscles in the inner ear that control the eardrum: the tensor tympani and the stapedius muscle. You see the tympanic cavity right behind the tympanic membrane. You see the auditory vesicles, the malleus, the incus, and the stapes. Okay. This shows you the 3 inner ear bones, the auditory ossicles. It shows you the auditory tube, which connects the tympanic vestibule to the pharynx or oral cavity, and it shows the external acoustic meatus as part of the temporal bone. Okay. And this gives you a real good view of the 3 bones, the 3 small bones. Again, you can see the malleus, the incus, and the stapes. And you see the 2 muscles that are attached. Okay. You can see the tensor tympani muscle, which connects to the malleus right there, okay, and pulls that and distorts the shape of the tympanic membrane, the eardrum. And you can see the stapes muscles, which connects to the stapes. There's your stapes right there. Okay, you can see the stapes muscle, which connects right here. And there's your 3 bones. Your malleus, malleus here, your incus, and your stapes. Okay, that's a fiber optic view of the same 3 muscles. You can see a little clearer here. You see the stapes with the big, like a staple hook right here. And then the incus, then the malleus ones are the first one. Okay, inner ear. Inner ear is where all the hearing stuff takes place. Receptors housed in the membranous labyrinth, within the bony labyrinth. There's a bony labyrinth where your receptors are. There's a vestibule, which is the area behind the tympanic membrane. There's a semicircular canal. There's a cochlea, which is snail shaped. There's a utricle, and there's a saccule. Okay, so here's the parts of the inner ear. The semicircular canals, which are these right here. The facial nerve, which is the top one right here. The one in the middle is the vestibular ocular nerve, number 8. Then there's a cochlea, which is your snail-like structure. This is your auditory tube, which connects the tympanic vestibule here, okay, and into the nasal pharynx, and equalizes the pressure on the inner ear. Okay, and here's how it connects. This is the nasal pharynx, so your inner ear connects into here. Okay, and this is where it equalizes the pressure, because the oral cavity is the same pressure as the external environment, and this equalizes the pressure inner as it puts a tube right into here where it can connect. So pressure can equalize behind the eardrum. All right, and this is with the utricle and the saccule. This is part of the semicircular canal right here. This is the cochlea right here. And your utricle, oops, come back. Your utricle is this area right here that's swelling, okay? And your saccule is the one behind it. So you have utricle, and the saccule. All right, who's paying attention? What's that first box?
Olfactory nerves.
Olfactory epithelium, that's pointing to that purple area.
Oh, okay.
Now it's pointing to what?
The nerves.
Actually, it points to olfactory nerves. Olfactory nerve, cranial nerve number 1. And what's the next box? It's pointing to this thing right here.
The bulb?
Oh, olfactory bulb. Okay, and then this is your
This.
that's the nerve tract. That's your olfactory nerve runs. Olfactory tract. And this is pointing to, no, that's pointing to. What was that point? Oh, I hit the wrong. The central, no, the central, it feeds into the central nervous system through the cranial nerve number 1. All right, and what's this? I could usually go down. So this arrow points to right here. What's that? The one that's going down, what's that pointing to? What's that part of that sphenoid bone called? With all the little holes.
Cribriform plate.
Perfect. That's called the cribriform plate. And that's pointing to epithelium again, the olfactory epithelium. And then you have 3 bones. You have this bone here that allow the circulation of air. This bone here and this bone here. So the first one points to that top bone, which is what?
Malleus?
Nope. Malleus is the inner bone of the inner ear.
Yeah.
This is the superior nasal concha. The next one is the inferior nasal concha. And the one in between them is the middle nasal concha. The vestibular complex is equilibrium. The vestibular complex is a part of the inner ear that provides equilibrium sensations by detecting rotation, gravity, and acceleration. Okay, so your ear can detect where you're spinning, It can detect the force of gravity being pulled down upon it, and it can affect acceleration when your body starts to move. Consists of the semicircular canals, the utricle, and the saccule. That's your vestibular complex. Okay. So here's the semicircular canals. This is the vestibule here. This whole area right between there. This is the vestibule. This is your semicircular canals, these big semicircles. And this is a utricle, and this is a saccule behind it. Okay. So each semicircular canal has a duct inside of it, each one of those tubes. The beginning of each duct is the ampulla. Within each ampulla is a crista with hair cells on it. Each hair cell contains a kinocilium and a stereocilia. A kinocilium is a large stereocilia, basically. Stereocilia are like microvilli, little cilia, a little bit bigger, and they detect movements. Okay? They're embedded in a gelatinous material called the cupula. The movement of the body causes movement of the fluid in the canal, which in turn causes movement of the cupula and the hair cells as the liquid moves. And the brain detects that movement. And that's what detects acceleration. That's what detects rotation. That's what detects gravity. Okay. So when you rotate your head, what's called the endolymph. Endolymph is inside the semicircular canals. So the endolymph in the semicircular canals begins to move. Okay, because it's in your ear. As you start to roll your head starts to move. That fluid is going to move also. As you move, fluid moves, it causes the endolymph to move with it. This causes the kinocilium, which is a large stereocilia, and the stereocilia to start to bend, to move, because the fluid pushes on it. And it moves those the cilia. The bending causes depolarization of the associated sensory nerve fiber. And that triggers the cranial nerve to fire. Okay? When you rotate your head to the right, the hair cells are bending to the left because your head moves to the right. So the fluid is moving to the right, so it bends your cells to the left. Okay, due to the movement of the endolymph. Remember, when your head moves, the endolymph is going to move opposite that direction as you got the force of inertia. So it bends the cells to the left. When you move in a circle, then stop abruptly, the endolymph moves back and forth, causing the hair cells to bend right and left. And that confuses you, and that's what causes dizziness. Okay, you ever get on you do the thing where you grab a baseball bat and you spin around and try to hit the ball? Okay, you get your head circling and the fluid starts moving and you stop. Now the fluid doesn't know where to go. It goes left and right. So the brain's getting this signal that you're going to the left and it's going to the right. So you confuse the brain, so you get dizzy and you lose equilibrium, lose your balance. That's what causes it. The utricle and the saccule, they're connected to the ampulla and to each other and to the fluid within the cochlea. The cochlea is the snail shell shaped. So hair cells of the utricle and saccule are in clusters, and those clusters are called a macula. The hair cells are embedded in this gelatinous material consisting of statoconia, which is calcium carbonate crystals. So this gelatinous material and statoconia are called otoliths. Otoliths sit on this gelatinous pad, and there's these crystals. And as your head moves, the crystals move. So if your head tilts back, the crystals slide back. If your head tilts forward, crystals slide forward, right and left. So you can tell where your body's moving. If you're in an elevator and it goes down really fast, the crystals stay on top and that weights decrease on top of it. And the brain tells it. When you stop suddenly, it compresses against it. So these otoliths move and they slide. Okay? And they're inside the semicircular canals, and you can tell. Anterior semicircular duct for yes. Lateral will tell you no. So anterior posterior gives you the yes motion. Lateral movement gives you the no motion. And the posterior duct is your head tilting as it runs in a semicircle. So that's how they're located. So as they spin, you can tell which are activated by which part of the endolymph and which part of the semicircular canals are moving. So there's your ampulla. Ampulla means swelling, a large area. So there's your ampulla, there's your utricle, and the saccule behind it. Okay, you have the endolymphatic sac produces endolymph, and the endolymphatic duct produces your endolymph. And there's your macula, which is where your otoliths are stored in the gelatinous material. Okay. So here's the cupula, and you can see this is the ampulla is filled with endolymph right here. So this is filled with endolymph. That's all this blue material. Okay, this is the cupula. Inside the cupula, you have these hair cells that are sticking up. Okay, those are the crista. That's the crista here, and then I have the hair cells that stick up. Okay. As that moves, the cupula bends. So again, if your head moves to the right, the cupula bends to the left. Because as you're starting to move, that liquid is actually stationary, so it moves the opposite direction. So the hair cells bend to the left, and your brain interprets that movement. So you can see when it moves back and forth, when you've been spinning around, then you stop, it's going to confuse those hair cells completely. Okay, that's why you get dizzy. Here's a close-up view of the cupula. Your hair cells. This is the crystal cells that respond, that are triggered by movement of the hair cells. Once those hair cells move in the fluid, it reaches a threshold and triggers an electrical impulse to send through the sensory nerve into the central nervous system. Okay, so these are different types of rotation. Okay, as you move your head to the right, fluid goes to the left. Move to the left, fluid goes to the right. At rest, it bounces nice and easy. But once those hair cells bend, that's what triggers the electrical impulse, and that's what tells your body what's going on inside of it. Okay, this is what we're talking about with the kinetococulum and the stereocilia. The stereocilia are big microvilli, and there's one at the very end which is really thick. This really thick stereocilia is called the kinocilium. Okay, and that's what bends for the, oops, go back. That's what bends when you get movement. This is the hair cell itself. You can see the stereocilia, and it displaces it and it stimulates the hair cell. Once that liquid once those stereocilia get displaced, move left to right, then it triggers the sensory nerve and it gets interpreted into the central nervous system. Okay, the vestibular complex in equilibrium, when you move up or down, like in an elevator, those otoliths we talked about, those little solid crystals, they rest on top of the macula. Okay, when you're moving upwards, the otoliths press down, so you feel the elevator going up. When you're moving down, the otoliths lift up, so you feel the elevator dropping down below underneath you. When you tilt side to side, those otoliths shift from one side to the other. They slide. Okay? And that's what it looks like. That's your inner ear. Those are the otoliths. These are crystals. And that's just what they do. And they sit on this gelatinous material. Okay? So you can see when the head moves, those crystals are just a big group of crystals. Okay? And they're going to slide. And when they slide, they put different pressure on different areas of that gelatinous material. And the gelatinous material is suspended by the hair cells with the kinetococulum and the stereocilia. Once these depolarize here, you get an impulse being sent to the brain that your body's moving. And it sends to the sensory neuron right here. Okay, but these are your otoliths. So you can see if you're in an elevator and you're going down, the otoliths put less pressure on the gelatinous material, right? Because gravity's pulling you down, but they're staying up. When you're going up in an elevator, it puts pressure against those otoliths, so there's more pressure on the gelatinous material, more pressure on the hair cells, and your body can tell. So that's what your body can tell if you're going up or down an elevator. You get that feeling. Roller coaster the same way. Okay? When you drop in a roller coaster, you can feel you're dropping, right? That's because these otoliths are being raised up at a very fast rate. And that's what's making you dizzy. That's what's giving you that feeling. When those otoliths lift up, there's less pressure on the gelatinous pad. Those hair cells are firing, saying, whoa, we're getting a feeling of going down, and the body's moving. That's what gives you that feeling of that negative G's, basically. Positive G's when it gets pressed up against it. Okay? So all these otoliths shift, and these are just those crystalline structures moving. That's how you determine motion in your ear. These otoliths on this gelatinous pad. That's what it looks like. And these are the otoliths, an SEM microscope, a scanning electron microscope picture of it. These are the statoconium. These are the otoliths. Okay? And they're just this pile of crystals that sits on this gelatinous matrix. And it tells you how you're moving because they're going to slide. When your head moves, these things slide. Okay? So neutral position, you can see gravity. You can see the otoliths are bounced right over the stereocilia and the kinocilium. Okay, when you lift your head backwards, what's going to happen to this little otolith? It's going to slide backwards. And as it slides, it distorts the hair cells. The hair cells say, we're moving, and it sends that signal to the brain, and it tells you which way your head's being tilted. Okay. Slick system, huh? Pretty neat. Sensory fibers from cranial number 8. Okay, the vestibulo-ocular nerve. It's synapsed with the vestibular nuclei, which is located between the pons and the medulla oblongata. So here's your vestibular ganglion coming from that area. This is your vestibular branch of the nerve. This is the cochlear branch, and it goes into the vestibular nuclei, which is between the pons and the medulla oblongata. And from there, it goes up into the cerebral cortex and gets interpreted as movement. Okay. So the vestibular nuclei integrate the sensory information from each side of the head. So the right and left sides of the head send information to the vestibular nuclei, and that sends it to the cerebellum and the cerebral cortex. And then you got motor nuclei within the brainstem and the spinal cord, which create movement to counteract or to balance the body, depending what the equilibrium system says it's doing. So the cranial nerves involved are 3, 4, 6, and 9. 11, accessory nerve. Again, the same thing. These are the nerves that are involved. This is cranial nerve number 3. You can see where they come in. Number 4, number 6, and number 11, the accessory nerve. And that goes into the vestibular nuclei, and part goes to the cerebellum, the other part goes to the cerebral cortex. And it goes to the superior colliculus and inferior colliculus relay to the cerebral cortex. Okay, so hearing, that's equilibrium, that's balance. Let's go another 10 minutes, and then we'll finish up this chapter the next time too. All right, so the cochlea. Cochlea consists of snail-shaped spirals. Okay, it looks like a snail shell. The spiral coil around a central area called the can't talk tonight. Modiolus. Modiolus are sensory neurons. Okay, the sensory neurons are associated with cranial nerve number 8. You have the organ of Corti. Okay, it's a structure in the cochlea that the inner ear that produces nerve impulses in response to sound vibrations. So inside the inner ear, you have this, the cochlea. Inside the cochlea, there's organs of Corti. So the cochlea takes that sound, goes to the organ of Corti, and they send that impulse in response to different sounds, vibrations that can be interpreted by the cerebral cortex as different sounds, different letters, different vowels, and so on. Okay, and there's your cochlea, your snail-shaped structure, and vestibular number 8. Okay, that's the one down below there that sends the impulse out. Sensory nerve. This is the inside of the cochlea. You can see the modiolus is these areas of the bone right here on the sides of it. Okay, this is the organ of Corti. Okay, this is the organ of Corti. It's that structure down below. It's that last little one right down below where the black line's pointing. Those are all organs of Corti right there. That little piece of, that little blue dot right there. Okay, those are organs of Corti. That's what interprets the sounds and gives nerve impulses depending on the type of sound that gets interpreted by it. Okay, but that's what the snail shell looks like inside as it winds up. It winds up, then it winds back down. Okay, so here's your inner ear. Okay, and that's what the cochlea looks like. Now inside the cochlea, there's this organ of Corti, and it sits right on the base of it here. And as the fluid flows over it, it bends or distorts its hair cells. Okay, depending on how much it bends or distorts, depending on what nerve is triggered. So here's your auditory nerve. Okay, here's your auditory nerve, comes up and fits right in the organ of Corti. Okay, so you got the inner hair cells, you got the cilia on top of it, outer hair cells of the organ of Corti, and your auditory nerve. You can see how it's built up right here. When these hair cells move, this is a tectorial membrane. This is the membrane inside the cochlea, and as the fluid moves inside it moves these hair cells, and it triggers different sounds, moves differently as it winds its way through this pathway of the cochlea, and interprets of different sounds. Okay. So each spiral consists of 3 layers. Okay, there's the scapula vestibuli, which is the vestibular duct, which is perilymph. There's the scala tympani, which is your tympanic duct, which consists of perilymph, and there's your scala media, which is the cochlear duct, which consists of endolymph. This is between the scala vestibuli and the scala tympani. That's the endos between them. So there's a basal cell membrane between each layer. The scala vestibuli and the scala tympani are connected at the apical end of the cochlea. It's all continuous snail shells. It rolls around. When it gets to the top, it just reverses, it comes back down, it spirals down around it. So it's all continuous. Okay? So the sense organs, organs of Corti, rest on the basilar membrane with the scala media. So it can be easily transmitted to the auditory nerve. Okay. So this is the cochlear duct, this is the vestibular duct, and that's the tympanic duct. And again, they all run up through it and they all go right back down the opposite tube. So it's all continuous. It's not different duct systems. It's one system, it's depending on which way it's going. Right? So the sound comes in, you see the sound, this is the stapes. Remember, you have the malleus, the incus, and the stapes. So here's the stapes at the oval window. That's where sound gets transmitted. Because that's transmitted to the tympanic membrane, your eardrum, goes to the malleus, to the incus, to the stapes. Stapes goes into the round oval window. Oval window feeds information into the cochlea. The cochlea sends this information to sound waves, and watch the purple arrow as it winds up around there. Okay. As it winds up around, it goes through the vestibular duct, and it goes up this vestibular duct and down the tympanic duct. And in between those two is the cochlear duct, which is where your organs of Corti is located. Okay, so remember, it's one continuous system, it's not different systems. So you can see one system's going up and one system just winds back down. So this is from the oval window. Okay, the oval window, again, is where the stapes meets, okay, into the vestibule. So that's where information comes from the eardrum. Okay, and it comes out at the round window. So it enters at the oval window, which is connected to the stapes, and it exits at the round window. Okay, you got your vestibular duct, your tympanic duct, and in between you got your cochlear duct, which is the blue right there. And in the cochlear duct, you have your organ of Corti, which interprets your sound. And that's in your cochlea. Okay, the organ of Corti is also known as the spiral organ. It rests on the basilar membrane where the nerves are, between the scala media and the scala tympani. Hair cells are in contact with the overlying tectorial membrane. This membrane is attached to the lining of the scala media. That's that blue area in between the two. Okay, so sound waves cause distortion of the tectorial membrane in there that stimulate the organ of Corti, the hair cells, and that determines what type of sound it is. Again, so there's the organ of Corti, that little dot right below it, because there's the cochlear duct is all the blue. The cochlear duct is the big space. The little tiny thing there is the organ of Corti, and that sits between the tectorial membrane and the tympanic membrane. Right? One has the envelope going up, then coming back down. And it's all a continuous system. So here you can see it being dissected out. You can see how the organ of Corti sits between the two layers. So here's your vestibular membrane, okay, which vibrates with different sounds. Okay, that's the tectorial membrane. Okay, and there's your organ of Corti. Sits right on the basal membrane, and all these hair cells interpret that sound and feed it directly into the cochlear branch of nerve number 8. Okay, again, tectorial, this is how it works, tectorial membrane, the outer hair cells. Okay, this is the organ of Corti right here. You have your basilar membrane, you have your inner hair cells, and then you have your nerve fibers that feed that information out. And that's what a light microscope picture it looks like of the organ of Corti. Okay, vision. Accessory structure of the eye, you have the palpebrae. Palpebrae is the eyelids. Okay, you have the medial and lateral canthus. Those are the corners of the eye where the eyelids come together. You have the upper eyelid and the lower eyelid. Where they come together at the corners, on the medial aspect, that's the medial canthus. On the lateral aspect, that's the lateral canthus. The palpebrae fissure is the opening between the upper and lower eyelids. You have eyelashes. Eyelashes contain root hair plexus. Okay, they trigger the blinking reflex. When something touches your eyelid, it triggers your eye to blink before any damage can occur to your eye. They're there to protect the eye. Okay. The conjunctiva is the epithelial lining of the eye. Right? That's your outer layer, protect the eye. You have glands in the eye. You have the glands of Zius, the tarsal glands, you have the lacrimal gland, and you have the lacrimal caruncle. I got my coverage of that. There. Got me covered by drink. All right. So looking at the eye, you have the eyelashes, which triggers a blinking reflex. You have the palpebrae, which is the eyelid. You have the palpebrae fissure, which is the opening between the upper eyelid and the lower eyelid. You have the medial canthus of the eye. You have the lacrimal caruncle, which is the bump in there. You have the lateral canthus of the eye. Okay. And the conjunctiva. The conjunctiva is the clear lining of your eyelids on the surface of the eye. That's the external epithelial lining. You have the lacrimal gland. Remember, the lacrimal gland produces our tears. Okay, it goes across the eye and then bathes the eye to help protect it. And you have the palpebrae fissure. The palpebrae fissure is the opening between the palpebrae. The palpebrae, the upper eyelid and the lower eyelid. And opening between them is the palpebral fissure. Again, the lacrimal gland is what produces tears. You can see the lacrimal gland is this gland right up in here. And all these little areas, you can see all the ducts of the lacrimal gland. Okay. And you have your lateral canthus, this corner, and your medial canthus, this corner. Okay. The lacrimal gland produces tears, goes through the lacrimal duct, and the fluid forms right here. And the fluid flows across the eye to protect it, okay, into the lacrimal sac. That's what collects the fluid. Then they go through this tube here, which is the nasolacrimal duct, into the oropharynx, up in the nasal cavity. That's it. When you cry, your nose runs because your tears are going into your nasal cavity. And it bathes the eyes and comes through there. Okay, these are the glands of Zias, okay, and your tarsal glands. Tarsal glands are in the palpebrae. Glands of Zias are sebaceous glands associated with your eyelashes. Okay, so basically we'll go review that a little bit. The palpebrae are your eyelids. Okay, they're connected to the corners called the medial and lateral canthus. That's what connects your eyelids. Okay. Eyelashes are on the palpebral border, help protect the eye. They trigger the blink reflex. And each eyelash is associated with the glands of Zias, which are sebaceous glands. Okay. The tarsal glands are in the inner lining of your eyelids. Okay. Those secrete a lipid proteins, basically, that prevent the eye from sticking together. So when your eye closes, it doesn't stick. That's what these glands help to produce. That lipid helps to protect the eyelids from sticking together. Okay. Now the palpebral fissure does what? What's the palpebral fissure?
It's the opening of the eyelids, correct?
It's the opening between the upper eyelid and the lower eyelid. And the upper and lower eyelid are joined by the medial canthus, by the side medial closest to the nose, and the lateral canthus farther away. Perfect. Okay. So again, here's your lateral canthus, here's your medial canthus, and this is your upper eyelid, this is your lower eyelid. And the opening between these is your palpebrae fissure. Okay. And again, we talked about the glands of Zias. Okay, those are the glands of your eyelashes. Those secreted a lipid product that keeps the eye. I'm sorry. Those are produce liquid help for the eyelashes. The tarsal glands are the glands of the eyelid that produce a lipid product that keep the eyelids from sticking together. So the conjunctiva, that's the outside lining of the eyelids. Okay, it's the outer lining of the eye. Fluid production prevents these layers from becoming dry and sticking. Okay. The palpebral conjunctive is the inner lining of the eyelids. The ocular conjunctive is the outer lining of the eye, because this makes one continuous epithelium. Okay, think you have the eyelid and you have your eye. Okay, and they're in contact with each other. Right? There's liquid between them. Okay, the inner lining of the eyelid, on the eyelid part, is the palpebral conjunctiva. The outer lining of the eye is the ocular conjunctiva. Let me see if I have a picture of it coming up here. No, not really. Let me go back. This is, okay, so this is their inner lining here. And this is the inner lining of the eye. You can see how they line together. So that inner lining of the eyelid is called the palpebral conjunctiva. The outer lining of the eye is called the ocular conjunctiva. Okay. For the eyelids, the glands of Zias are for protection and lubrication. Those are associated with the eyelashes. Okay. Glands of Zias are sebaceous glands. Okay. Associated with your eyelashes. The tarsal glands, those are the glands in the eyelids. Those ones produce that lipid protein that keeps your eyelids from sticking together, sticking to the eye. Okay. You have lacrimal glands. We talked about lacrimal glands produce tears. and they're located in the superior lateral portion of the eye. So upper and away from the midline. So that when you tear, the tears go across the eye, protect it, and drain into the inferior medial aspect where the lacrimal sac is. And that collects the tears and pushes them into the nasal cavity. The lacrimal caruncle glands produce thick secretions, which are located in the canthus area, right in between at the medial canthus. Right. So eyelids, an infection of the tarsal glands result in a cyst. When your eye has a cyst, that's what becomes infected is the tarsal glands. Okay. Those are the glands of the eyelid. Okay, that's where your eye becomes sore and it's kind of hard to focus. An infection of the other glands can result in what's called a stye in the eye. Right? Okay, the lacrimal apparatus, how you produce tears. The lacrimal apparatus is responsible for producing, distributing, and removing tears. Produces the lacrimal gland, which produces your tears. Has the lacrimal duct, which carries the tears away from the gland into the superior lateral portion of the eye. Has the lacrimal canaliculi, which are the canals, those are the ducts, little canals. Okay, it flows across the eye to the inferior medial portion, which is your lacrimal sac. Lacrimal sac goes through the nasal lacrimal duct to produce the tears into the nasal cavity. And that's where your nose always runs when you cry. Okay. Again, this is a picture we looked at before. You can see the lacrimal gland. You can see the canaliculi here, or the lacrimal ducts. So tears are produced in the superior lateral region. Okay, and they flow across the eye to the inferior medial portion of the eye. Okay. And here you have your nasolacrimal sac, which collects the tears and distributes down into the nasal cavity, okay, through the nasolacrimal duct. And that's how the lacrimal system works. Okay. Tears are produced by the lacrimal glands. They flow over the ocular surface, like we said, across the eye, and they flow into the nasal lacrimal canal, which is a foramen, which is an opening. The foramen enters into the nasal cavity. Okay? So like I said, when you cry, tears flow across your eye, run down your face, and they come out through your nose. That's why when you have a runny nose, every time you cry, because that's where the tears are exiting from. All right, so who's paying attention? What's that point to?
Lacrimal glands?
Lacrimal gland, that's what does the lacrimal gland produce?
Tears.
Tears. Okay, what's the next one down point to?
Lacrimal gland ducts.
Perfect, lacrimal gland ducts or the okay, where am I at? The lacrimal gland ducts, okay, as it produces the tears, they run across there, and then it goes into the ocular surface, flows across the surface. Remember, it flows from superior lateral, which is up the top region, across the eye to the inferior medial aspect. Okay, and what's that structure being pointed at on the next one down below that?
Lacrimal punctum.
Lacrimal puncta, that's like the expansion down there. And then if this was pointed, those little tiny tubes are often called what?
Canaliculus.
Perfect. Lacrimal, sorry. Canaliculi. Canaliculi just means a little tiny canal. Lacrimal canaliculi. And those flow into the
Nasolacrimal duct.
well, they flow into the lacrimal sac. This region right in here. They flow into the sac first, and from the lacrimal sac, they flow into the nasolacrimal duct, right? So that's how your tears flow. The lacrimal system goes from the lacrimal gland, okay, through your lacrimal ducts, flow across the eye. Okay, the lacrimal put-down tears is swelling right here in the eye. Okay, they go to the lacrimal canaliculi, which are little canals that fill this lacrimal sac. Goes in the lacrimal sac, goes through the nasolacrimal duct into the nasal cavity, and that's how it exits through the nose. All right, the eye consists of a sclera, the cornea, pupil, iris, lens, an anterior cavity, posterior cavity, and there's 3 tunics. Tunics are just different layers around the eye. They're the fibrous tunic, a vascular tunic, and a neural tunic. And if you had to guess, you would say the fibrous tunic has a fibrous tissue that helps support the eye. The vascular tunic controls the blood flow to the eye, and the neural tunic is where the retina and the nerves run from the eye. And then you have the retina. Okay. So here's your eye. And we said we have the posterior cavity. This entire thing here is the posterior cavity. This is your posterior cavity. Okay. It's filled with what's called the vitreous body. That's what helps support the vitreous body, is a gelatinous material, helps support the shape of the eyeball. Okay. When you're doing forensics and you want to determine the time of death, if people wrap the body in, say, an electric blanket, people put the body in a freezer to try to keep the temperature change and try to alter the time of death, can't do it. There's potassium levels inside the posterior cavity decay at a certain rate once the body dies. So we just dissect the patient, take the eyes out, open this up, determine the calcium and potassium levels in here, and you get a perfect time of death. So all these forensic shows where they tell you that someone puts them in a freezer or some of that, they get fooled. Not a chance. They determine the potassium levels of the vitreous body and determines the time of death. We have got also the anterior chamber. Okay, here's your anterior chamber. This is the front part. Okay. You have the lens, which focuses the light. You have the pupil, which light goes through. Cornea, which is the outer layer of the eye. Iris. Iris determines your eye color. They're the muscles that control the amount of light that's allowed to get inside the eye. And you have your posterior chamber. That's filled with aqueous humor. So you have an anterior chamber, a posterior chamber, and a posterior cavity. Okay, this is your posterior chamber right here. Okay, that has aqueous humor. That has filled with aqueous humor. Okay, and these are 3 tunic layers we talked about. Remember, we had a fibrous tunic, a vascular tunic, and a neural tunic. And these are true there. The outer layer is a fibrous tunic. Okay, a connective tissue, fibrous tissue. The other layer is your vascular tunic with your arteries and veins. And the layer is your middle layer here, which is your neural tunic. This makes up the retina and all the photoreceptor cells. Okay, that allows you to see, that allows your eye to respond to light. Okay. So the outer layer of the 3 tunic layers is the fibrous layer. It makes up the sclera and the cornea. The sclera and the cornea are continuous. They're the exact same epithelial layer. Okay. When the sclera reaches the opening of the eye, then it's called the cornea. Okay. So the visible part of your eye is the cornea. After it goes back behind that, it's the sclera, but it's all one continuous layer. It's just called different because of its location, because it's a visible portion of the eye. So the cornea is a modified sclera. It allows you to see through it. It provides some degree of protection to the eye. It provides an attachment site for the extraocular muscles and contains structures that are associated with focusing the eye. Okay. And here you go. This is the fiber tunic area. This is your fiber tunic. Again, it's your cornea and your sclera. Okay. And again, you see the sclera coming down here. And right when you have the opening of the eye, it becomes the cornea. So here's the cornea. This is cornea, and this is sclera. So it's all one continuous portion. It's just called differently when you have the opening of the eye. It's modified so light can transmit through it. But it's the outer layer of the eyeball. Does that make sense? Okay, good. And then behind the cornea, you have your anterior cavity with your anterior chamber and your posterior chamber. So you have an anterior cavity and a posterior cavity. Then you have an anterior chamber and a posterior chamber, which is the anterior posterior chamber is part of the anterior cavity. Okay, so it's a little confusing, but this is your posterior cavity right here. This is the back cavity. And this is your anterior cavity in the front. The anterior cavity has 2 divisions, an anterior chamber and a posterior chamber. That's what's divided up. Okay. So the second tunic layer is the vascular tunic. That's your blood vessels, your lymphatics, your intrinsic eye muscles. Okay. They regulate the amount of light that enters the eye. Okay. It secretes and absorbs aqueous fluid, which is your aqueous humor. So by secreting that aqueous humor, it controls the shape of the lens by putting pressure up against it. So it allows the lens to focus the eye on the focus the light coming in on the photoreceptors, and it allows you to focus and clearly see an image. Okay, so it regulates the amount of light enters in, and it's the shape of the lens. So it focuses the light differently to what you can see. Okay, and that includes your iris, which is the muscle that controls it, the ciliary bodies, and the choroid. Again, this is your vascular tunic, which is the second layer under the fibrous tunic, and it has the choroid, ciliary bodies, and the iris to help support the shape of the lens and the amount of light that enters the lens. And all that's involved with focusing your eye. The iris of the vascular tunic is your pigmented layer. This iris determines your eye color, whether blue eyes, green eyes, brown eyes, okay? Iris determines your pigmentation of your eye. So it consists of blood vessels, pigment, and smooth muscles. The pigment of the iris determines your eye color. Smooth muscles contract to change the diameter of the pupil. Again, you're changing the diameter of the pupil, allowing more light or less light to enter. The ciliary bodies and the choroid of the vascular tunic. The ciliary bodies consist of ciliary muscles that connect to suspensory ligaments, which are connected to the lens. Okay, they pull on the lens to change the shape of the lens to allow it to focus for far away or for near sight. The choroid is really vascularized. Okay, it's the innermost portion. The innermost portion of the choroid attaches to the outermost portion of the retina. So your outer portion of the retina attaches to the innermost portion of the choroid. Okay, so you have the fibrous tunic, the vascular tunic, now you have the neural tunic, which is your inner layer. This is the innermost of the three layer. The neural tunic is also called the retina. The retina has two layers. It has a pigmented layer, which is your outer layer, and then the neural layer, which is the nerve cells, where the images of sight is transmitted. Those are your inner layer. So the pigmented layer comes first, then the inner layer is the neural layer. The retina has two types of cells with two different functions. It has rods and cones. Okay, your rods are used for night vision and to see from the peripheral of your eye. Your cones are used for color vision, for very accurate visual recording what you see. So two cells, rods and cones. Rods are night vision, cones are color. Okay, so here's your neural tunic. And you see there's two layers. There's a neural layer, which lays underneath here, and there's a pigmented layer, which just forms your retina right here. And both those form the retina, the pigmented layer and the neural layer. Pigmented layer is your inner layer. The neural layer is the outer layer. So when light enters the eye, this is light coming in, travels through the cornea. Okay, this is the pigmented layer right here. Okay, and it travels to the cells. These are your cones, and these are your rods. Okay, so it travels through the cones and the rods. And on the lateral light microscope, you can see the different layers here. You can see your pigmented layer of the retina, rods and cones, bipolar cells, and ganglion cells. Ganglion cells are cell bodies that connect it. So you remember your rods and cones. Your rods are night vision. Cones are color. They're the ones that see color. So that's why if you see something like a dark green car at night, it could be black, could be blue, could be other. You're going to see it the same color. You're going to see it as a dark color because you can't see color at night because your cones are active during day vision, during where there's light. Okay. So when light shines through, this is where it enters the eye here. You have your bipolar cells, synapses with your rods and cones. Okay, these are the rods here. These are your cones over here. They can take that information to the pigmented system, which interprets the data and sends it into the optic nerve. Okay. So the neuroturnic, that's the retina. Okay, there are rods and cones all over the retina. 100% cones in the fovea centralis area. Fovea centralis is a spot in the eye where you have your main focus. Okay, those are 100% cones. That's where you focus for detail, for clarity. Okay, when you're working on a patient, suturing somebody, something like that, you're using the fovea centralis to focus in your central area. They're 100% cones. So your best color vision is when an object is focused on the fovea centralis. Okay, in the optic disc area, okay, there's 0 rods or 0 cones. Okay, that's where the optic nerve enters the eye. There's no rods or cone there. That's your blind spot. Everybody has a blind spot. Okay, so the fovea centralis is 100% cones. The optic disc, where the retinal nerve enters, has 0 cones and 0 rods. Okay, there's no vision there. That is what's called your blind spot. Okay, because you can't focus anything in there. Okay, so here's the fovea centralis. This is your main area of focus. When you focus there, you have 100% cones. That's very accurate. That's your color vision. This is your optic disc right here. The optic disc is where the retina, the optic nerve enters into the eye. So information can go into the optic nerve. So you can see where the optic nerve enters the retina, there's no rods or cones because the nerve's there. And then it spreads out into the retina. That's where the information from the retina goes out of the optic nerve into the lateral geniculate nucleus, into the occipital lobe of the brain. Okay. Is that making sense? Fovea centralis is where your main focus is, 100% cones. The rest of the eye is all rods and cones, except for the optic disc, which is where the optic nerve enters. There's 0 rods and 0 cones. This is your blind spot. Okay. So again, this is this is what you see with a fiber optics. This is your fovea centralis. Okay, that's your main focus area. Your main focus area is 100% cones. Okay. Where the optic nerve enters, okay, so the retina is your optic disc. That optic disc has 0 rods and cones and no vision there. That's right, everybody has a blind spot. Okay, and that's your blind spot. When something is focused on that area of the retina, you will not see an image. It will disappear on you because there's no way to transmit that information. Chambers of the eye. Remember, there's 2 big chambers. I should call them cavity. An anterior cavity and a posterior cavity. The anterior cavity is divided into the anterior chamber and the posterior chamber. Okay, the posterior chamber of the anterior cavity is filled with aqueous humor. The posterior cavity has a vitreous chamber, and that is filled with vitreous body. That's a gelatinous material thick that holds the shape of the eyeball. Again, so here you see the posterior cavity, which is filled with your vitreous body. Here you see your anterior cavity, which has an anterior chamber and a posterior chamber. Both the anterior and posterior chamber are filled with aqueous humor. The posterior cavity is filled with vitreous body. Okay, is that all making sense? It really doesn't point it very well, but those are the divisions. Okay, so the anterior cavity has aqueous humor. The aqueous humor is secreted by cells at the ciliary body. Okay, they enter the posterior chamber, posterior of the iris. Okay, it's still in the anterior chamber though. the end of the anterior cavity, the end of the posterior chamber, flows through the pupil area, enters the anterior chamber, flows through what's called the canals of Slem, and then enters back into the venous circulation. So it's a constant flow. Okay. So this is the anterior cavity. Okay. The aqueous humor is produced in the posterior chamber, flows through the pupil, through the canals of Slem, into the anterior chamber. Enters the anterior chamber, canals of Slem goes into the venous circulation. And that's how it circulates. Okay. So here's the pupil. This is your anterior chamber up here. This is your posterior chamber. Okay, flows out up into the across the pupil, into the anterior chamber, through the canals of Slem, into your venous system. The vitreous body. Vitreous body is in the posterior chamber, posterior cavity. I'm sorry. Okay, gelatinous body in the posterior chamber. Okay, that supports the shape of the eye. It's a gelatinous material. Supports the position of the lens. Supports the position of the retina. Okay. The aqueous humor can flow across the vitreous body and over the retina. So your vitreous body is a thicker material and it supports the shape of the eye. Okay. And pushes pressure against the retina to keep the retina from detaching. So it pushes the retina up against the back of the eyeball. So here you can see this is the posterior chamber and this is filled with vitreous body. Okay. This is what maintains its shape and all this pressure in this area to maintain the shape of the eye, maintains pressure on the lens, and maintains pressure on the retina to stay attached to the different layers. Aqueous humor is if this fluid cannot drain through the canals of the Slem, pressure builds up, and that's what causes glaucoma. So remember the aqueous humor flowed from the posterior chamber over the pupil into the anterior chamber, into the canals of Slem, into the venous blood circulation. If the canals of Slem get blocked, if you block the canals of Slem, that aqueous humor cannot flow. Therefore, pressure builds up in the eye, and you cannot focus your eye, and it causes blindness. And that's how glaucoma works. That's what they do when they do the vision test for glaucoma. They get your eye number, they put little weights on your eye, and it measures the pressure that's being exerted on your eye. If it's too high, we know the canals of Slem are blocked, and that's the first signs of glaucoma. That's how they check for it. Okay, so that's how glaucoma works. So now the vitreous body, remember the vitreous body is the thicker stuff, it doesn't flow. Okay, if that's not the right consistency, the pressure is reduced against the retina. The retina can come off the posterior wall. This is called a detached retina. Detached retinas are extremely painful, and you can lose vision in that eye. Okay. If you have a detached retina, one of the treatments after they reattach it is you cannot change pressure for 9 months or so. Which means if you're in 29 Palms, you cannot travel to the low desert. You can't change pressure. Okay, once they detach and put that retina back, any pressure change on your eye can cause that retina to reattach. So if you have a detached retina, plan on spending 9 months where you're at, because you're not going to be allowed to change the pressure that's exerted on that eye. Okay. The lens. The lens is just like a camera lens. It focuses the image on the photoreceptors of the retina. That's what it does. It's very concentric layer of cells. So layer after layer after layer. And the tension dispenser, you change its shape, which changes its focus. What causes it change in shape is tension, the suspensory ligaments, and contraction or relaxation of the ciliary muscles attached to it. And the change in shape allows you to focus far away, focus close up. Okay? As you get older, you lose the ability of those ciliary muscles to contract and relax. That's why a lot of older people wear glasses. The lens can't focus anymore very far away or very close up. Okay. So here's what you're talking about. This is the retina. Okay, this whole area here, this layer here, this is the retina, this inner layer. If the pressure in this vitreous body holds that retina against the choroid layer, if that pressure changes, gets less, the retina can move away from this layer and become detached. If the retina is detached, no signal from that area can be transmitted to the optic nerve. Okay. Again, reattachment can be done, but then you cannot change the pressure on it. Now, if you have the aqueous humor, remember the aqueous humor is this area right in here. This is all aqueous humor, and this is aqueous humor. Okay, and it throws out through these canals of phlegm right here into your venous system. If this becomes blocked, this fluid, this aqueous humor cannot flow out. It builds up pressure, puts pressure onto the lens, puts pressure onto the sclera, and it causes the lens, the inability of the lens to focus. That's glaucoma. That's what glaucoma is. It'll build up pressure in the eye. Okay, again, you can see a little bit of top view of it here. You can see if this pressure builds up, it puts pressure on the lens, puts pressure on the cornea. If this pressure builds up or decreases, it decreases pressure of the holding the retina to the optical wall. Okay. So how light enters your eye? Light waves pass through the cornea. Remember, the cornea is continuous with what part of the eye? The cornea is the part where the eye's open. Then behind that, the cornea becomes what?
The sclera?
Sclera. That becomes your sclera. Okay. As it passes through the cornea, it goes through the anterior chamber. The anterior chamber then goes through the pupil, where the pupil determines how much light comes into the eye. Then it passes through the posterior chamber. So anterior chamber, pupil. Behind the pupil is a posterior chamber. Then it passes through the lens. The lens changes shape by the ciliary muscles and focuses the image you're looking at by changing the shape of the lens. Okay, so the lens focuses the image on certain part of the retina. Okay, the part of the retina that image is focused on, the cells depolarize, and they transmit the message from the retina into the optic nerve, cranial nerve number 2. Okay, so here's how it goes. This is your eye. Okay, so the eye passes through the cornea. Okay, then it passes into the anterior chamber. Then it goes to the pupil, which determines there how much light comes in. Okay, then it goes to the posterior chamber. Then it goes onto the lens. The lens changes shape and focuses image so it hits a certain part of that retina. Okay, if that image is focused on the fovea centralis, what does that mean?
It's a blind spot?
No, that's not the blind spot. The fovea centralis is what?
Oh, the focus.
Focus. That's 100% cones. If it focuses on the fovea centralis, it means there's plenty of light. It means you're going to see the max amount of color and detail. Your night vision that will not focus on the fovea centralis, because the fovea centralis is only cones. And cones only see with lots of light during daytime or external light and color. Your rods see your dark vision at darkness. Okay. Now, if that were to focus on the optic disc, what would you see?
That's the blind spot. Right?
That's the blind spot. You would see nothing. There are no rods and no cones in the optic disc area because that's where the optic nerve enters the eye. So rods and cones can't exist there. So if the lens focuses it on the optic disc, you will not see the image. And everyone has a blind spot. Okay, after it focuses that, it focuses onto the retina, transmits through the vitreous, through the posterior chamber, I'm sorry, and onto the optic nerve, cranial nerve number 2. Okay, this goes through with the vitreous humor, which is this whole area right in here. Okay, so once it goes through the retina, cones require light to be stimulated. That's why they see color. So the cones require light, the rods do not. At night, you still have a small amount of light. You don't have any light at all, you're not going to see anything. Okay, but at night, when there's a small amount of light, the cones deactivate, and the rods become activated. That's what you can see at night, but you cannot determine color at night. So with forensics, if we have a witness that describes they say it was a green car, it was at nighttime, you know, it's either a blue car, a green car, a dark car, you know it's a dark color because they cannot see green at night. You can only see black and white at night. The pathway, okay, information arrives at the visual cortex of the occipital lobes. Remember, eyes, sight is focused onto your occipital lobes, auditory is focused onto your temporal lobes. Okay, there's the crossover information of the optic chiasm. We talked about that. The right eye goes from the optic nerve into the optic chiasm, which goes to the left side of the brain. The left eye goes through the optic chiasm and goes to the right side of the brain. Okay. So here's your vision, here's your visual field. Your right eye goes to the left side of the brain. Your left eye goes to the right side of the brain. Okay, it passes through the optic chiasm, the optic tract and the optic nerve, and then it comes to the quadrigemini, which is your superior colliculus and your inferior colliculus. The visual goes to the superior colliculus. Okay, that's the one that would determine if you saw a flash of light, your head would turn towards that flash. That's your superior colliculi. Okay, so the superior colliculus send that information to the lateral geniculate nucleus, which is located here, and then that goes into the optic region for the visual cortex.